Okay. What are we doing? Where am I?
Thank you for more random things you're throwing in. Thank you. What's on this follow-up?
The topic for this week and next is permutation groups. What is a permutation? You know?
The different order of the elements, so you shift the elements along a bit.
Yes. So
I hope I know it's my project.
doesn't matter. Not needed now, but so that we don't forget.
When you get your head on your fucking idiot.
What's wrong with my head?
No, me.
Okay, so a permutation.
Have you seen the pictures? Yes.
And you have a set, okay? No matter what set X it is, it can be. So you're thinking a finite set, which is what Laura said, you know, but it can be infinite. But then it's also still just a reshuffle of places, really. And so the reshuffle of places is a bijection of the set onto itself. Okay? So if we permuted in this room, then I would get Jordan's place, for example, and Ilan would get, you know, and so on. So a bijection means that everybody's assigned exactly one, and exactly one is assigned to everybody else. So I would be assigned Jordan's place, for example, and Jordan somebody else's. But you can't have two people in the same place, and you can't have two places for the same person. So bijective means onto and one-to-one at the same time. Okay. In fact, if X is a finite set, then being onto already forces it to be one-to-one and vice versa. But if it's an infinite set, then you have to check both conditions, that you don't map two elements on one and that you don't miss out any element. Because you could have, for infinite sets, you could have mappings that fail one condition but satisfy the other. So that's the idea. Now, when you have a finite set, X, then, you know, have you seen this notation perhaps with Killian before? So, for example, if X is A, B, C, to follow the book, so that I don't confuse you more, then, okay, so if A is mapped to B, and B is mapped to A, and C is mapped to C, okay, this is denoted by kind of, you put A, B, C and at the top, and then the images go below B, A, C. Have you seen this before? Yeah. Okay. So this is a notation which we'll be using a little bit, but it's not. But slightly superfluous if you write too much in some sense. So we'll introduce a different one in a bit. Okay. So for a group, when we look at the group or anything like that, really, it doesn't matter what the elements of the set X are called. Okay, the structure on it, if you take it, okay, so when you look at all the permutations of a certain finite set, then it doesn't matter what the names of the elements are. So we can always think that we're looking at numbers 1, 2, 3, 4 to some n. So that's what we'll be doing. And the definition is that the symmetric group on n elements is, well, it's a group. I'm saying it's a group, but I'm just promising it's going to be a group, but group called Sn of all permutations of the set 1 to n with composition as the operation. So I should promise that it's going to be a group. So I should prove that it's a group, so that's theorem 5.1. Okay, it's a bit just patience. I mean, maybe it's not quite clear what's going on in terms of what's going on, but we'll see in a bit what it is. Right. So Sn is a group with n factorial elements. This is how students in America recognize that something is a theorem. It's in a box.
It's the word theorem, not given. Americans are stupid.
Well, not all of them. Maybe on average. Okay, proof. So what am I claiming? I'm claiming two things. One, that Sn is a group, and the second thing is that it has exactly n factorial elements. So which one do you want me to prove first?
Systematically, Sn is a group.
Sn is a group. Okay, so what do you need for something to be a group? As an identity. Okay, so what is the identity?
Where everything's mapped to itself.
Yes, exactly. So is the mapping that maps every k to k, which goes from 1 to n. Okay, so if you compose this, then with anything, then the mapping you get is the one you started with from both sides. Okay, something that sends 3 to 7, and then 7 to 7. When you compose it, so it still sends 3 to 7. So that is indeed the identity. What else do we need? Inverses, yes. But there is an inverse map, right? To a bijection, every bijection has an inverse mapping. So does that sound familiar?
Yeah.
Okay, so that's every bijection. And then we need associativity. Of composition. Is that obvious?
Somewhat.
Okay, so when you Okay, what does that mean? So, okay, so F composed with G composed with H. When I do this, should be the same as this. Okay.
Mapping after mapping after.
Yeah, and it actually is. So when you take X, okay, then this by G composed with, oops, H is mapped to G of H of X, okay, and this by F is then mapped to F of G of H of X. And then when we look at the right-hand side, we start with any element X. Now, by H, this is mapped to H of X. And this, by F composed with G, is mapped to F of G of H of X. So this and this are equal, which proves associativity. Okay, so we have a group. And the order of Sn is an exercise. If I remember correctly, it's one of the submission exercises. As a hint, you can prove it by induction, but everything that has some N in it, that already smells of induction. So it is indeed a group. And it's called, remember, which has disappeared, that's called the symmetric group. Now, the next definition is what is a permutation group. So permutation group is any subgroup of a symmetric group. Okay. So in a way, this is there is a like we'll see later that every group is a permutation group, kind of. But there is an important kind of idea that, and I tried to stress it before, that you should see the elements of a group as things that act on a certain set. Right? So they, for example, the symmetries of a triangle, and things like that. So here you have the symmetries of the most symmetric set, where no matter how you mix them around, you get a symmetry. Okay, and that's the symmetric group. Does that make sense? So when you can map any number to any other number, as long as you don't map two numbers to the same number, it's a symmetry of the set. So there is no special structure. If you have a square, it's the dihedral group or the dihedral group. In the square, you can't do whatever you want with it. You can't. If you have two adjacent vertices, you can't map them to opposite vertices diagonally, opposite vertices. So there is some structure. So you can't. So not every mapping is a symmetry. But when you just look at n numbers, then everything is a symmetry, and that's the most extensive or whatever, the richest kind of group. At the same time, you can look at, so when you look at, so example, example that we'll come back to probably next week is, so the dihedral group. So when you look at the group of symmetries of a square, okay, when you number the vertices 1, 2, 3, 4, and you look at all the possible, so the dihedral group, of the square, somehow induces on the vertices 1, 2, 3, 4 a permutation group. So, for example, when you do a what's it called? I keep forgetting. Not the rotation. Yeah, the reflection about the vertical axis. You get e.g. vertical. Is it readable at all? Not axis. Axis. Reflection. So 1 goes to 2, 2 goes to 1, 3 goes to 4, and 4 goes to 3. Yeah? And that's an example of a permutation group. Immediately you get a permutation group just in the square. Okay. There's an example 5.2 in the book. I'll just show it like this. I'm too lazy to write it. So what you get is, so this is just arbitrarily almost selected 3 elements from S5, and they happen to form a subgroup. So it's a subgroup of permutations. I don't know where it comes from. I should have checked where it comes from. It might be something defensible. Okay, so there's an example where there are indeed subgroups of the symmetric group. The proof is that it multiplies as in the Cayley table. Okay, then there is a remark. So the remark is when you have, so for 2 permutations, sigma and tau, what is sigma tau? And some people think that it's do sigma first and then do tau, and some people think it's that do tau first and then do sigma.
Sigma after tau.
Well, both conventions are used by mathematicians. So to stick to what the book does, we'll do that. This is like x first do tau, and then do sigma. Okay? So composing first tau, then sigma, which is how you write composition of mapping, right from right to left usually, because you want, because, so the idea is that if you do tau of x and then sigma, and that's sigma composed with tau of x, and so but you could as well play the other one, right? So some people would even write x tau sigma for this. So the x starts first, and what you do with it, and then what you do with it. There are some authors who write it in this way. We'll use it. We'll write it like this. So this is. Sometimes you will see. Now the problem with this is that GAP does it the other way around. Sage. GAP is a module of Sage that does the groups. So in Sage, well, you have a note to about this in the handout. So Sage just warning. Sage, not like this. Well, so this left to right, right to left, that's a big complication because mathematicians just don't agree on a single concept, and you have to be careful what's being used. It's just like that. Okay, example of a phenomenon. Okay, let's say sigma is 1, 2, 3, 4. Goes to 4, 1, 2, 3, and tau is 1, 2, 3, 4, goes to 2, 1, 4, 3. So what is sigma tau? Okay, that means doing tau first, and then sigma. So how does one do that? 1 goes to 2, goes to 1. Okay, so 1 goes to 1. What's next? 2 goes to 1, goes to 4.
Oh, yeah.
3 goes to 4, goes to 3. 4 goes to 3, goes to 2. Okay, so this is how you compute things in this notation. Tau sigma, that means I do sigma first, and then I do tau. So 1 goes to 4, goes to 3. 2 goes to 1, goes to 2. 3 goes to 2, goes to 4. And 4 has to go to 1. So let's just check. 4 goes to 3. No. What have I done?
3 goes to 1.
3 goes to 1, yes. 3 goes to 2 goes to 1, and 4 goes to itself.
3 goes to 4.
Yes. Okay, so this is how it works. At the same time, this shows that sigma tau is not the same as tau sigma. So the symmetric group in general is not abelian. Okay. Sometimes it is abelian. When is it abelian? When n is 1 or 2, I think. I think when n is 3, it's already not. Okay, just some simple cases are abelian. Okay, now an important thing is, I mentioned before that this notation is very long. Okay, so cycle notation is the following. I'll do definition by example. So you start with the 1. And I'm looking at the sigma. Okay, so this is the sigma above. 1 goes to 4. 4 goes to 3. 3 goes to 2. 2 goes to 1.
This is why
tau is, start with the 1. 1 goes to 2, 2 goes to 1, end. What's the least element we've not used yet? 3. 3 goes to 4, 4 goes to 3. Okay, so this is called the cycle notation of permutations. Now, how do you multiply in this notation? So here, sigma tau, without looking up what it is, if I wanted to do it in this notation directly, okay, I start with the 1. Now, tau first, sigma second. Okay, so 1 goes to 2, goes to 1. That finishes it. Now, 2. 2 goes to 1, goes to 4. 4 goes to 3, goes to 2. Aha, so that's it. And then 3 goes to 4, goes to 3. Right. So one typically in the cycle notation doesn't write the cycles of length 1. So you just write 2, 4. 2 goes to 4, 4 goes to 2. 1 and 3 are not there, so they just go to themselves. And one last example, when I'm doing the multiplication the other way around, sigma first, so 1 goes to 4, goes to 3. What's next? 3 goes to 2, goes to 1. 2. Where does 2 go? What am I doing first? Sigma. 2 goes to 1, goes to 2. And 4, there's nothing else left. So again, you can write it just as 1, 3. Okay. That seems simple enough? Oh, yeah?
Like one in my project readings, I'm going to just go over this. And in the application that I'm using, it uses exactly the opposite of that. So they write down the ones that stay the same and don't write down the ones that swap. Really, really confusing.
Okay. Yeah. Now, if you're a bit unsure about these calculations, the exercise series, page 92. The first couple of exercises are go from the usual notation to the cycle notation, from the cycle notation to the usual notation, multiply some cycles, and things like that. Compute the inverse. Okay. Oh, that's very interesting. In fact, no, we've not. So, so what's sigma in? I'm running out of ink. Just take it. What's the? But you can think of how you find the inverse of the sigma.
We're still using the cycle.
Yeah. That's the only thing that's left now. So 1 goes to 2 because above 2 goes to 1. And 2 goes to 3 because 3 went to 2. And 3 goes to 4 because 4 went to 3. And 4 goes to 1 because 1 went to 4. Simple.
All right.
Any questions? Is he on the phone? You're talking about Jordan, are you talking about the groups or are you on the phone?
Yeah, no, I was talking about the group.
Not quite clear.
Who would I be calling a little bugger?
Right, so if you end up with one cycle, it's called a cycle. So the precise definition is a cycle of length k is a permutation. Stop sentences with a capital. Is a permutation for which there exist some elements, some k elements, such that when you do A1, you get A2. When you do sigma on A2, you get A3, and so on. AK minus 1 is AK, and then the last of these elements goes to the first. And as we've just seen, sigma is then denoted like this. Okay? That's just the definition of the cycle. So not every permutation is a cycle, but this one is a cycle, whereas this one is not a cycle. Okay, 1 goes to 2, 2 goes to 1. And oh! It would be a cycle in my stupid definition, except sigma of x has to be x for all other x. What to say? But I realized when I was trying to show that something is not a cycle because it doesn't satisfy something. Now I realize it does actually satisfy my wrong definition. Okay, so this doesn't satisfy this definition because what you want is one cycle like this, and then all the other elements map to themselves. So, for example, here as well, sigma tau is a cycle because 2 maps to 4, 4 maps to 2, that's the cycle, and the rest is fixed. And here the same, that's a cycle as well. So this is what permutations are like, more or less. Now, we know how to do products of cycles. The easiest case, though, of products of cycles is when the cycles are disjoint. So 2 cycles are called disjoint. Well, if the sets of the AI's are disjoint, okay, so if they don't share an element. This is a stupid way of formulating it. There's a better one in the book. Among their respective AI's. Okay. Killian will kill me. Killian, where are you? Kill me. I'm giving you wrong definitions. Well, it's not wrong, but it's just not. It's not very precise. Now the thing is, with disjoint cycles, we've got this one particular. Okay, so it's kind of so. Okay, 1, 2 times 3, 4 okay, is, well, 3, 4 times 1, 2. That seems almost like a non-statement, because the cycle notation for permutations already uses this fact that if you have 2 cycles, it doesn't matter in what way you do, because this bit only shuffles the 1 and 2, and this bit only shuffles the 3 and 4. So it doesn't matter whether you first shuffle the 3 and 4 and then the 1 and 2, or the other way around. Or in other words, one almost proving, I should call it an observation, but it's called proposition 5.8 in the book, is that if sigma and tau are disjoint cycles, then they commute. Except I can't write. Then they commute. Sigma tau equals tau sigma. Okay. No, I'm not doing the proof because it's clear. I mean, you can do proof. Okay, if you want to do a longish formal proof, look at page 85 and go through it. But it just uses lots of letters to write what I've just said. Okay, they just don't. Now, what is interesting, though, and is not much harder, is this theorem, which tells you that every permutation is every permutation is the product of cycles, which justifies the cycle notation, because that means is a product of disjoint cycles. Oh, every permutation in Sn. It's been slightly sloppy, perhaps, in what we've been doing, but from theorem 5.1, we've only been looking at the symmetric group on a finite number of elements, so no infinite permutation groups. There are infinite permutation groups, but we're not talking about them at the moment. So that's also, I mean, this is not true for infinite groups, for example. I don't think. No, because you might need infinitely many cycles, and that's not a product. You can't do an infinite product in groups, really. Okay, what is the proof? Okay, so the proof, again, when I started thinking about the proof, that reminded me that I need a finite permutation there, because what you do is so the first cycle, you can start with 1, then look at what sigma does, then look at what sigma does in the sigma, and so you go, and then at some point you close the cycle, and then is cycle x1, And then you're left with fewer elements than you started with, okay? And so the second cycle, you take I is the minimum of elements that are in, so numbers 1 to n, but not in x1. So the least element in the set of integers 1 to n, okay, this is my notation. Have you come across this before? No? Doesn't matter. So when I write n in square brackets, without, and it makes sense in the expression that I've written it in, then I mean the positive integers 1 to up to n. So I look at those ones. X1 is the ones that I've already put into a cycle. So I look at all the remaining numbers that I've not yet put into this cycle. Okay, and I start with that number, and I do the sigma on this, sigma squared on this, and so on. Then at some point the cycle closes, and so on. So this is then cycle x2, and then I can continue, and it stops because every time I take out some elements, you don't understand what I mean. Yeah. But what really goes on is when you recall how we were first writing, okay, what is sigma in cycle notation, or tau, and that's what we did. Okay, so are you still reading? Because I'm just about to replace it with something else for a second.
Yeah.
Okay, so this is what we were doing. Tau. What is the first cycle? Well, 1 goes to 2, 2 goes to 1. That goes in the first cycle. Now I'm only left with 3 and 4. So 3 goes to 4, 4 goes to 3, it's the second cycle. If I had a larger permutation, then I could need more disjoint cycle in here, but this is what I've just done. So this gives me a product of disjoint cycle. And there's nothing fancier in proof than this. So the process stops after a finite number of steps. Because n is finite. I'm only starting with a finite number of elements, and I take some out, and I take some out, and I take some out, so at some point I will have nothing left. Okay. How much time is left? Not much time. Okay, so this is probably a good point to stop. We've done virtually. We've got here in the book. So we mark 511, which reads, from this point forward, we will find it convenient to use cycle notation to represent permutations. When using cycle notation, the identity, so the identity you don't really, how do you do it? Because the identity is just 1, 2, 3, 4, all the cycles. So, but we said that we don't write the cycles of length 1. So we wouldn't write anything. So in that case, we'll write just a cycle for the 1. But it's not, it's just a convention. It doesn't really matter much. Any questions? Good. So then tomorrow, what we'll do is look at transpositions. These are cycles of length 2. And then they somehow define a subgroup which is exactly half of all the elements in the symmetric group. It's called the alternating group. So that's the plan for tomorrow. And then next week, we should look at dihedral groups seen as permutation groups. Right.